Hello and welcome. In today's video, we're going to be going over topic 4.9, the antiderivative. So, a very big topic, or in general, sometimes we're given rates of change. The world around us is ever changing, and that's why we have the derivative. But to represent change. But now we're going to develop what if we are given a derivative or a rate of change? How do we go from that rate of change to the original function? And this is the idea of the antiderivative. So a function f, capital F is more specifically, is called the antiderivative of lowercase f on an interval I if the derivative of capital F is equal to at little f, or lowercase f, for all x in the interval I. So it's really just what is going to be the undoing factor for the derivative. So where we're going to start out here is, what is the derivative of all of these following functions? Well, the derivative of x cubed plus 5, trivial, 3x squared. X cubed plus 1/2, 3x squared. Again, we're just adding a constant there. Then we have x cubed, again, 3x squared. And then we have x cubed minus 100,000, maybe a bit more challenging. Nope, still 3x squared. So we have this one derivative here, but it has an infinite amount of antiderivatives. So what we're going to see is that we're going to have to apply a constant for this general idea of the antiderivative. So I'm going to ask now, what is the antiderivative of 2x? Well, the answer to that question is, what function do we have to take the derivative of to get 2x? And the answer is x squared. But what about x squared plus 5? X squared plus 7? X squared plus pi? All of these values have the derivative that is 2x. So for the answer, we just get x squared plus the constant of integration, which we're going to learn what that means much later on. But this would be our answer, as this would encompass any one of these constant values. All right. So now we want to find the antiderivatives of the following. So what do I have to take the derivative of to get sine? Well, if I take the derivative of cosine of x, I get negative sine of x. So we know that we can just multiply by a constant on the outside of the derivative. So if we multiply by -1, then the derivative will become sine of x. So the answer for the antiderivative of sine, so capital F of x, is going to be negative cosine of x. Well, for this b, we normally think of the natural log of t being the antiderivative, or of being the derivative that gives 1 over t. But 1 over t has a lot more domain than just that single factor there. But what if we just real quickly define this as a piecewise function? So we're going to say lowercase f of x is equal to the piecewise function of negative x for x less than 0, and 1 over x, for x greater than 0. There we go, fix it. Well, now we can take a look at this and we can think to ourselves, well, I know that the derivative that gives me 1 over x, that's just the natural log of x. But what about the derivative that's going to give me negative 1 over x? Well, that is just going to be the natural log of negative x, because we can use the taking the derivative of it. Using the chain rule, we get 1 over negative x times by negative x. Or sorry, negative 1. Well, what this shows us is the derivative of the natural log of the absolute value of x, whether x is negative or positive, is equal to 1 over x. So, we say the antiderivative, or in this case, f capital of x, is going to be the natural log of the absolute value of x. For c here, if we're going to take the antiderivative, let's start with what happens when we take the derivative. Well, we bring the power down, and then we multiply by the power. Well, if we were looking to undo this, what we need to do is divide by 1 over n plus 1 times by x to the power of n plus 1. And we can show that this is going to be equal to x to the n if we just take the derivative. So we're going to decrease the power by 1. So we get x to the n, and then bring the power out front, so we get n plus 1 over n plus 1, which that's just 1, so we can clearly see that the f of x in this case is going to be 1 over n plus 1 times by x to the power of n plus 1. Alright, so here is a lot of anti-differentiation formulas. So I'm going to let you pause the video here, look at it. Alright, now that I've given you an opportunity to look at it, let's try and find the antiderivatives of the following. Well, what is it called? So, we're looking for the antiderivative of 8. Well, the derivative of 8x is 8, so we know f of x in this case must be 8x plus a constant c. Well, for this next one, if we can use our inverse power rule to increase by the power of 1 and then divide by that power, and we see that f of x in this case is going to be equal to x to the power of 8. We know the derivative of sine is cosine, so the antiderivative of cosine is sine of x. And the derivative of e to the x is going to be e to the x plus c. Or sorry, the antiderivative of e to the x is e to the x plus c, because the derivative of e to the x is e to the x. And always remember your constant of integration. Alright, now we are going to start talking about the exact antiderivative. So sometimes, whenever we're taking the derivative, saying we're taking the derivative of x to the 5th plus 5x squared plus 3. When we take the derivative of this function, we're going to lose a constant. So we're going to get 5x to the 4th plus 10x. Well, the issue is whenever we go to take the antiderivative of this, we don't know the value of the constant. So earlier when we were doing general antiderivatives, we just added on the value c. But if we want to know the exact value of the original function, we need to find that value of c. So what that's going to look like is we're going to find the exact value of antiderivatives given the conditions. Well, what is the antiderivative of 2x? or the general antiderivative. So f capital of x is going to be x squared plus c. But we also know that f of 0, or capital F of 0, is equal to 3. So 3 is equal to 0 squared plus c. So we find out that c is equal to 3, which allows us to find our original formula, which is f of x is equal to x squared plus 3. For this next function here, the antiderivative is going to be 1/3 x cubed plus x squared. Well, if we plug in plus a constant c, well, now we have to plug in the value of x of 1 and set that equal to 5. So we get 5 is equal to 1/3 times by 1 cubed plus 1 squared plus c. So 5 is equal to 1/3 plus 1 plus c. So finally, subtracting this over to the other side, we get c is equal to what looks to be 3 2/3. So for our exact antiderivative here, we get f of x is 1/3 of x cubed plus x squared plus 3 2/3 for our answer. Well, now that we have this proof for finding the exact finding the exact antiderivatives, we can now apply this to the sciences, because sometimes we are given a function, let's say, or we're given a velocity, but now we also have the tools to evaluate the function if we're given its position at a certain point. Find its new position at a new point if we're given the velocity or the acceleration, and that's what we're going to do. So suppose that the acceleration of a car is given by a is equal to 3t squared plus 2t plus 5. Find the velocity at t is equal to 3 if v of 0 is equal to 4. Alright, so we are given information about the velocity at a certain point. So what we're going to do is we're going to say v is going to be the antiderivative of velocity, or of acceleration. So the antiderivative of 3t squared, that's t cubed. The antiderivative of 2t is t squared. The antiderivative of 5 is plus 5t. And then we have to add a constant of integration. Well, we know at t is equal to 0, the function is equal to 4. So 4 is equal to 0 plus 0 plus 0 plus c. So we know our constant is c. So finally, we can now plug or set up the exact antiderivative here, which is going to be t cubed plus t squared plus 5t plus 4. Now we have to evaluate this at t is equal to 3. So v of 3 is equal to 3 cubed plus 3 squared plus 15 plus 4. So v of 3 is equal to 27 plus 9 plus 15 plus 4. That sums to 19, that sums to 28, 27, that sums to be 55 if my head math is correct. Alright, so we know the velocity at time 3 is 27. I suppose I should have given like feet per second, but I don't particularly care. But this would be its formula. Alright, well, now we want to find the displacement of the particle at t is equal to 5 if s of 1 is equal to 3. Well, now we have to take the antiderivative of this. So s is equal to, we have to increase the power by 1, so we get 1 over 4 times by t to the 4th plus 1 over 3 times by t cubed plus 5/2 of t squared plus 4t plus c. Now we have to solve this for when t is equal to 1 and it's equal to 3. So we get 3 is equal to 1/4 plus 1/3 plus 5/2 plus 4 plus c. Getting a common denominator on this right side, we are going to get, I suppose 12 is going to be the one that we're shooting for. So we are going to get 3/12 plus 4/12 plus 30/12 plus 48/12 plus c, and that is equal to 36/12. All right. Now what we have to do is we just have to solve for c. So c, well, let's sum up everything on this right side. So 3 plus 4, that's 7. Plus 30, that is 37. Plus 48, that would be 85/12. All right, plus c, and that's equal to 36/12. Now, all we have to do is subtract the 85. So 85 minus 36, we get 49/12. 49/12 is equal to c. So we now know that s of t is equal to 1/4 t to the 4th plus 1/3 t cubed plus 5/2 t squared plus 4t plus c, which we now know is 49/12. All right. What do we do now, you may ask? Well, what we're going to do is we are going to now plug in the value of 5, which is going to give us a very absurd number. So we get 1 over 4. So 5 times by 5, that's 25. Times that by 5, it's 125. Times that by 5, that is 625. Plus 5 cubed, which is going to be 1/3 times by 125 plus 125 halves plus 100 plus 49/12. All right. Now what we have to do is, once again, probably try and get into everything common denominators, but I'm going to go to my calculator here, because sometimes it's okay to use calculators. And after punching that in, we get a value of s of 5 is equal to 364.5. And that's our answer. Well, I hope you all have enjoyed and found this video informative, and if you did, please make sure to like and subscribe. Have a wonderful rest of your day.